In this video, which is the final one for chapter 14, we are going to discuss the two major types of alloys. As always, you are going to need something to write with, and you're going to need a notebook. Once you have those things ready, let's go. Okay, so we should probably start off by describing what an alloy is. An alloy is a solution made of two or more metals, a homogeneous mixture. What you do is you take a bunch of metals, you melt them all together and keep stirring them until it becomes homogeneous, and then you let it cool down. Once that happens, you get one homogeneous solid. That solid is your alloy. Now, the properties of any individual alloy are based on, most importantly, the properties of the base metal, right? So, for example, steel, which is an alloy, the properties of steel mostly are based on the properties of iron, which is the base metal that steel is made from. Okay, so that you also have to talk about how much of the metals are present. So, not just the base metal, which I have listed here, but even the different things that you add into alloy with it. Again, for something like steel, if I just combine iron and carbon, I get the alloy steel. If I throw in things like nickel and zirconium and zinc and chromium, I wind up getting stainless steel. And the properties of that stainless steel will differ based on the percentages of each of those things in that mixture. And if you want to look this up online, you could find hundreds upon hundreds of different stainless steel mixtures that all have different use cases based on exactly what you need the substance to do. And the last thing that we need to know about an alloy is whether or not its structure is substitutional or interstitial. And that's what I'm going to go over in the next couple of slides. So a substitutional alloy is exactly what it sounds like. We are taking the metal solid, the metal lattice, and we are replacing atoms of our base metal with atoms of the new metal that we're using to make the alloy. Gold is a good example of a substitutional alloy. What we're doing is you have a pure sample of gold. Pure gold is what's called 24 karat gold. If you start pulling individual gold atoms out of the lattice and replacing them with copper, replacing them with silver, replacing them with platinum, then you get the different gold alloys that are used to make jewelry. They just take the place of the gold atoms in the solid, and that makes up your alloy. The way that you make a substitutional alloy is that the elements that you add have to be of similar atomic radius, right? So that's why, for example, gold and copper and silver and platinum tend to work very well, because if you look up their atomic radii, they don't differ by that much. So it's easy to just plug one in, and there you go. And the properties of the alloy, again, based on the base metal that they come from, but it will be affected by the other metals you put in. So it will be somewhere in between the base metal and the other metal that you use for your alloy. The more of the other metals you have, the more its properties will be like that of the other metal. That's why, for example, gold, 24 karat gold is extremely soft. 10 karat gold is only 10 parts out of 24 gold. The other 14 parts are other things. So 10 karat gold tends to be much, much harder and less easy to bend and deform, which is why it's commonly used in jewelry. The other type of alloy is what's called an interstitial alloy. So substitutional is when you pluck an atom out and put a new atom in to replace it. You substitute it. Interstitial is almost, again, what it sounds like. What you're doing is you have your crystalline lattice for your metal, and then you start inserting things in the middle of the lattice. So like you have 4 parts, one northeast, southeast, northwest, southwest, and then you stick something right in the middle of those. So you fill the gap, kind of. That's an interstitial alloy. Now, because you're trying to put something in the gap formed from other different lattice points, that's something you put in has to be extremely small in comparison to the atom that you're working with as your base metal, right? So interstitial alloys, radii are really, really different. Smaller things fill into the gap. This is steel, for example. Iron has a fairly large atomic radius. Carbon is really, really tiny. So you go putting carbon in, carbon will stick in and it will get into the middle of that lattice. And what that does for its properties, well, if you start sticking things in the middle of an empty lattice, it's going to make that substance harder. It's going to make it less malleable. There's a reason why steel is a lot more durable than cast iron. You don't use cast iron to build skyscrapers. You use steel because steel will not bend, it will not deform, it is less reactive than normal iron is. It has a much higher melting point than normal iron does, right? All of these things that give you the properties you want in a building, stability, structure, right? That's one of the reasons why I use an interstitial alloy. And this last slide is just going to give you kind of an image of what these look like based on your base metal. So on the left, we have a pure metal. This can be whatever metal you'd like. We'll assume for just sake of argument that this is iron, right? So pure elemental iron. If I go plugging in tiny little carbon atoms into this gap, I get steel, right? Because steel plugs in those holes, makes it much more rigid. That's our interstitial alloy. If instead I take out some of the iron atoms and replace them with chromium or nickel and all that sort of things, I get other alloys. These are substitutional alloys. All right, so again, some of the things I'm going to ask you to do, I'm going to ask you like, here are two elements, and I'll give you their atomic radii. Would they form an interstitial or substitutional alloy? I would say what type of alloy is best for this specific application based on what you want to do, right? And things of that nature, how I'm pretty much going to test you on that. But that is it for chapter 14. When I see you guys next, we'll be working on chapter 17, which is equilibrium.